Once we agreed that we have two different types of type systems, which pretty much decide are divided whether the type is decided during compile time or the type is decided during runtime. Next question we need to ask ourselves is, what are the advantages and disadvantages of each of these two systems? When we want to compare these two types of type systems, we see that there are differences. Again, these differences came in from the audience, and we sometimes we say it's better, sometimes we say it's worse. We're not claiming that one is better than the next. We're just saying there are differences between the type systems. So, for example, if we want to compare static and dynamic type systems, so the first thing that came to mind is safety, and what is meant is actually type safety, and the meaning of that is that we are normally when we program, we're unhappy to get all kind of type errors. But the truth is that what we're getting to something like reliability. That's what we're getting here, which is they hear the word safety, but the word reliability might be better suited. Reliability might be better suited for this. And in a sense, what we're getting is we don't have all kind of commands running with wrong types or in wrong fashions or in wrong ways. So we are getting what's called type safety. And static does give me that. Dynamic, not really. In a sense, during the dynamic typing, so we're going to run during runtime, and during runtime, we're going to have a crash that could have been avoided if we would have just run the program using a statically typed language. If we try to add two types and it doesn't work, or the compiler does not know how to do that, so what would happen is that during a statically typed language, the compiler is going to yell and say you can't do that, and then we're obviously going to be unhappy. But at the end, we're going to get a code which is much more reliable because we have to get it past the compiler. While if we're talking about a dynamically typed language, and there's nothing in the during the compile time that allows me to know that there is a problem, except all kind of massive unit testing, and test it with this and test it with that, and do a lot of unit testing, a lot of code testing, a lot of runtime testing to check if I have an error. Because if I do, it's going to happen during runtime, which is not a good thing. So that's the first thing that came to mind. The second thing that was brought up by the audience was efficiency. What does that mean? Um, we already mentioned that types are there, whether we're talking about a dynamic type language or a statically typed language. Whether we talk about explicit typing or implicit typing, it's still there. And therefore, somebody has to actually run the system behind the scenes. Now, if we have a statically typed language, it just means that during compile time, the commands are checked, the commands are executed, and we don't have to actually check things during runtime. While if we use a dynamically typed language, so during the entire uh, interpretation or runtime of the program, we need to go and we have to say, okay, this fits that. Well, this is a type this, so therefore do that. And therefore, all these deductions that are based on the type have to be deferred to the runtime, which makes it less efficient. In all the benchmarks that I've seen, static typing with good compilers, obviously, pretty much are used as the benchmark for the speed of things like C plus C or whatever, those kind of languages. And this is one of the reasons. Now, it doesn't mean that dynamically typed languages are slower per step. They could be more efficient for other reasons, and therefore they can run faster. But as far as the type system is concerned, statically typed languages move a lot of computation to compile time, while dynamically typed languages move them to runtime, and therefore, as far as this topic is concerned, they are less efficient than statically typed languages. The next thing that was brought up by you guys was the maintenance costs. What does that mean? We all know the famous software engineering graph that looks like pretty much like that, and this is the cost, this is the time, and this is the cost, right? And the cost of a bug, increases exponentially, not linearly, as time goes on. The minute we go out of the, let's say, out of production, out of the development into production, the cost of a bug is a lot more expensive than catching it during the development time. So the further down we are in the development cycle, the cost of the bug increases. If we catch a bug during the initial compile time, the cost is very low. If we catch it during integration, the cost is higher. If we catch it during production, the cost is very high. So, in a sense, if we are able to move the time for catching type system bugs, variable type-based bugs sooner, the cost is actually less. So the maintenance cost or the cost of development is actually less when we talk about statically typed languages as opposed to dynamically typed languages. Now that doesn't mean that if I want to develop some kind of throwaway code or like for one-time use, then I say, oh, but let me use a statically typed language instead because the costs are higher. That's lower, sorry. That's not necessarily true. Because if you're doing something for a one-time piece of code, just to, let's say you want to merge two databases or two data sets, and you just right, so you slap together some kind of it's called a throwaway code, and it just runs. So you don't really care if the types are this way or that way, as long as there's no real errors, and you can always do it again if you have to. And you're not, it's not something that can be done again if you made a mistake. But if it can be done again, so you say, okay, I'm going to slap together some piece of code, and I'm gonna just so I don't really care. That's what I mean. That's what I mean by cost. Therefore, I call it maintenance costs. I didn't call it just cost, because when it comes down to cost, you can say, oh, the cost of a dynamically typed language is less because I can, as I said, slap together something and just run it and get it over with. All the bash scripting and that kind of stuff. Even Python scripting. I'm not talking about Python programming. Python scripting is a lot of times just simple throwaway codes, and therefore I don't want to say cost, but I'd rather call it maintenance cost. The maintenance cost of um, statically typed languages is usually lower because in the development cycle, as we said before, the bugs are moved to an earlier time set. And if we look at our picture from before, the bugs are moved further this way and they're caught in a statically typed language. And they're moved further that way in a dynamically typed language. And again, I don't want to put an exact marker because there's no exact marker. But the further left that we have the bugs being caught, the cheaper it is. And the further right that we have bugs being caught, the more expensive it is. And therefore, we want to actually move things that way, not this way. I've seen in a lot of companies in industry that they might go and create a simple proof of concept piece of code in a dynamically typed language. And the idea is that we have a simple way of putting together a proof of concept. It doesn't have to work efficiently. It doesn't have to work. It doesn't have to work exactly correct. It could make all kind of mistakes. It's not going to be a developmental cost like we see in production, because the idea just is to prove that something is doable. It's a proof of concept piece of code. It's in a sense, it's a throwaway piece of code. So a lot of companies will go and develop those kinds of pieces of software in a dynamically typed language because the idea is rapid prototyping or something. But afterwards, when management goes and says, okay, go ahead, gives the green light, so they stop and they start doing everything in a statically typed language. They might go back and do it in Java or C# or C++ or C or one of those, because the idea is that besides the efficiency, the maintenance cost of afterwards maintaining the software over time is a lot cheaper when you do it using a statically typed language as opposed to a dynamically typed language. Once we said that, so we look at the next column, writability. So again, in writability, it's exactly the same idea. Well, we have all kinds of proof of concept codes, right? Proof of concept pieces of code, which are, as I said, the point is just to slap together something and show that it's doable. So writability makes life a lot more writable when I use a dynamically typed language than a statically typed language, as opposed to when I want something to be cost effective, I might actually use a different type of language. I don't know if you have ever heard of things like a hot swapping of code, that in a sense, while the program is running, I want to take out something and put in something else. I don't want to shut down the program and rerun it. I want to actually switch something while the program is running. So in a statically typed language, that's, I would say, impossible, but and the idea behind dynamically linked libraries in a sense is giving that capability that I can go and say, okay, let's switch the DLL, and then when the program loads the DLL, it's going to get a different part of different piece of code. But that's not necessarily a hot swapping of code because DLLs are a lot of times loaded before the program begins. I mean, you can load dynamically load a DLL language using some kind of assembly code saying load library, like a Win API or something, not assembly, Win API, a load library, and you load a DLL, and that's a very difficult way of getting hot swapping of code. While if we're using a dynamically typed language, we can very easily go and say, okay, just take a piece out, put a piece in, and the types would work out. If the types need to change, they will change. For example, if we go and look at a piece of code in the dynamically typed language, and suppose that we have, let's say, someplace we write something like C is equal to 3, and then somewhere down the code, down the piece of code, we swapped in some piece of code, and over there C was equal to hello by chance, right? Then there's no problem because the runtime is going to infer that this is an integer, and it's going to re-infer during runtime that this is a string, and that's okay. There's no problem with that because we are actually behind the scenes we are holding a type table, and in our type table we have our C, and we have is type of, right, the type, and at first we had it as an integer, and now we have it as a string, and that's okay because we're running all that during runtime. So we actually do hot swapping of code very easily. The fact that we're using interpreters usually is a helper, but that's not necessarily required. You can actually go and use other types of methods, but idea is that we don't have to make sure that everything fits in from the beginning and just say, oh, and crash if it doesn't work out. So all those things add to writability that we actually mentioned before. However, when it comes to readability, so it's the other way around. Readability, here we have a readability offset, some kind of tension between readability and writability, and we say, okay, so the readability of statically typed languages is actually better, and the readability of dynamically typed languages is actually worse because you're not sure at any point in time what is your type. And when I say readability of the language, I don't mean the language as a whole. I just mean to say the type system part of it. You can actually pick it up and say, people can't get up and say, oh, Python is way more readable than C. Well, that's possibly true. But when we talk about the type system, it's actually less readable because in C, I know exactly what's going on, while in Python, I actually have less idea of actually what's going on. So those are advantages or disadvantages of the type system. There's one more interesting difference that I would like to mention right now. That's the eval code, the one that you can actually put a string in here, and you put a string inside, and then the eval turns that into running code, which is in compiler courses, we actually deal with that. We actually write a compiler of a language with the actual language. You write a compiler of Lisp using Lisp, which is a functional language, and the eval is what is actually doing the work, which means we take some kind of code, a string, and we actually execute the string. Now let's think about this kind of code in a statically typed language versus a dynamically typed language. In a dynamically typed language, there's no real problem. It's almost the same like hot swapping of code. What happens is that when you get to the eval, and we actually turn this piece of code, this piece of string into code. So whatever it says inside, it executes. And if the types match, great. And if they don't match, we just update our type table. But in statically typed languages, you can actually break the type system because the compiler has no way of checking the insides of this eval statement during compile time. It actually might not know it at all. I mean, just think of a piece of code that says, tells the user, please input a piece of code, and the user inputs a string, which in the sense is code, and then we eval that piece, that string, that str. So the compiler can, during compile time, will not even know what the str contains, and it has no way of checking if the type system is, in a sense, reliable. We have type safety or efficiency or whatever it is. It has no way of actually doing that during compile time, which is a very interesting point. While for dynamically typed languages, it's actually a very mute issue. It's no big deal. It's no different than any other piece of code that actually will get executed whenever we get to it. And if the types match, great. And if they don't, we just update the type table. So eval is something that dynamically typed languages can take more advantage of than statically typed languages, which might need all kinds of convoluted ways to actually get that thing to execute.